every single titration is going to follow the same idea. I have my little chart. Okay, every trial I'm going to have two charts. I got a known and I have an unknown. Okay. Now, for this value here, and I'll switch over here for this guy, I have my molarity, I have my moles, and I have my volume. Okay. Now this, for my known, in this case, my known is going to be right here. Okay. And I'm simply going to get that known, I am going to mass it out on a scale. It is a solid. It's one of the first things you're going to do in this lab. Then my goal is to figure out this guy. This is my unknown. This is a liquid. Okay. It is a purple liquid. Okay. It is also considered a strong oxidizer. It has all of these oxygens to which it can give away, and this is one of the standard things it drops down to when given an opportunity to give away its oxygen. Either way, so this is my known. Okay, it's going to be in a beaker below the below the burette. This stuff here is going to be in the burette. Usually are known. I usually put the known in the burette. In this case, because this is a liquid, this is a solid, I'll put this in the burette. So in this case, my volume of my unknown will be in the burette. Okay, and I will have a start for this stuff. Okay, and I'll have an end, and I would want to, at that point, for every trial, record off my burette, my start, and my end. My goal is to find the molarity of this unknown compound. Okay, I already know, because of my solid, this stuff is a solid, I can just convert this stuff directly to moles, and I can therefore plug that right in here. Okay, now I will need to add some water to my solid in order to dissolve it, just to get this thing to run. Does it, so I can at least stir it, dissolve it. Does it matter how much I add? No, not really, because I'm not concerned with the molarity. All I'm concerned with is how many moles are actually in there. Now, I don't want to add a ton of volume to dilute it completely, but the amount of water I add in this case does not matter. I'm speaking of the oxalate here. It's a solid. We're going to mass it. We're going to know the moles. So the molarity of that is not a concern for us at this point. The volume really is not a concern for us at this point. What I want to find out is how many moles. Well, I know how many moles are in there, but at this case, I want to find the moles of my unknown. This is a 5:2 ratio. So when I reach my equivalency point, okay, when I reach my equivalency point, it is going to be a 2:5 ratio to these moles. Now, how do I find my molarity? Well, I'll have my volume that I used. This volume will go right here. Make sure you convert to liters. I will have my moles at this point at my 2:5 ratio. I will then be able to calculate based on molarity equals my moles per liter, calculate my molarity of my unknown compound. Okay, in this case, my permanganate. Now, my equivalency point. How do I know when I've reached my equivalency point? So an equivalency point is an important concept, and I could just type that out here. This is going to be what's called the equivalency point. Okay, and that is where you could say it's where your moles are equal, but it's where your stoichiometric ratio is equal. And for this particular lab, what I'm doing is I am dropping the permanganate into the oxalate. This stuff, as I mentioned, is an extremely purple substance. This stuff is clear. Okay, this stuff is clear. Carbon dioxide will bubble off. You'll see bubbling. So what happens here is that as this stuff drops in, the oxalate converts it to a clear substance. So you will see purple dropping in, and then you'll see purple disappearing. as soon as your faintest amount of purple sticks around, that means all of these, the amount you've added, they have equalized or been equivalent by a 2 to 5 ratio. So our equivalency point is reached when no more purple is available. Now this reaction takes place in acidified solutions, so you're going to want to follow the directions on how to set the reaction up because it needs to have a certain environment to work. Okay, but in the end, you will do several trials at once and run one after the other. They'll go very quickly. So one of our main things we'll learn in lab is that when you, just for lab technique, is just as easy to run 3 trials at once as it is to run 1 trial. So I could easily run, when I mass this thing out, the oxalate, get 1 sample, 2 samples, 3 samples, 1, 2, 3, and then when I run my titration, just do 1, 2, 3, one after the other one, and I'd have 3 of these setups in my lab notes to detail out the start, finish, start, finish. Of course, when you end one, that'd be your start for your next one. Okay. Now, also one important thing here is that the permanganate, you're going to want to use the same permanganate throughout the entire lab. There are several jars there. Make sure you take one that's got plenty of liquid in it, and that you can use for the entire lab. So let's recap here quickly. We will go, first thing we'll do is use the oxalate. Again, at this point, when I convert the solid to moles, it's actually sodium oxalate. Make sure you use the sodium oxalate molar mass to convert to moles. Then I'll have my moles of my oxalate, and then I'll titrate my permanganate into it. At that point, I'll know my moles at a 2 to 5 ratio of my permanganate in my sample. Divide by the volume of that sample, which is gotten by the titration, to get your molarity. That will then be used for the next reaction. How much iron do I actually have? Well, at this point, I know my molarity of my known. My knowns now flip. This is my known. Now again, that's purple. This is clear. So when I react these two things together, the purple is destroyed or converted to, again, my common Mn2+ compound. This is iron 2+. This has got a slight yellow tint to it. You will see that. Okay. Once I'll have my molarity of my permanganate. I'll have my volume of my permanganate. I'll find the moles of my permanganate. 1 to 5 ratio will give me my moles of my iron. At that point, I have one last calculation to do, which is the percent by mass, and that is on the first slide. Here, that will fill this mass of iron. Divide by the original will give you my percentage. You want it to be as accurate as you can. When you're running several trials at once, the first one can be relatively quick and dirty, is what most people in the field call it. And then you realize, okay, it's going to take about 25 milliliters to run this. Okay, then the second and third trials, you can drop in, if it takes 25 milliliters, you drop in 23, and then the last 2 or 3 milliliters, you're really going drop-wise to just barely get it to turn. Okay. Other than that, that is what's called this particular lab, the determination of iron sample permanganate of the permanganate. Now here it says, as far as anything else they want you to do here is unknown vial. It is very important to record down which vial you took your unknown sample from, because you need to be able to compare what you got. They want you to do a percent error. How far off are you from the actual value? Okay, that's the main thing. Check with the original instructions as far as whether these questions or other things you have to do to complete the lab. Thank you.